Hello students, welcome to second lecture of chemical equilibrium. I will start with recap and then we will discuss more other concepts which is important in chemical equilibrium. We started with definition of equilibrium, and then I told you what is equilibrium. It is basically a state of balance between two opposing forces. That is what an equilibrium in a broader sense means. In case of chemical equilibrium, we are talking about equilibrium in a chemical reaction, suppose A to B, where A is a reactant and B is the product. There is also tendency to go from B to A, and that is your reverse reaction. Here two forces are first rate of forward reaction and the second is rate of reverse reaction. As in case of other equilibrium, when rate of forward reaction is equal to rate of reverse reaction, we have condition what is called equilibrium. Chemical equilibrium or physical equilibrium. So, two balancing forces are rate of forward reaction and rate of reverse reaction. When they becomes equal, you have condition of equilibrium. Then we talked about your type of equilibrium constant. Constants, and I introduced terms like Kc, Kp and Kx. For a reaction A to B, we define what we mean by Kc, Kp and Kx. So, Kc is your concentration of B by concentration of A. Concentration of B by concentration of A. Kp is pressure of B by pressure of A, and Kx is mole fraction of B by mole fraction of A. Here I am talking about equilibrium concentration of B and equilibrium concentration of A. So, Kc is your ratio of equilibrium concentration of B divided by equilibrium concentration of A. Similarly, Kp is your equilibrium pressure of B divided by equilibrium pressure of A, and similarly Kx is your equilibrium mole fraction of B divided by equilibrium mole fraction of A. For a reaction like so, if you look at this reaction, what does that mean is A mole of reactant A reacts with B mole of reactant B. So, this is your number stoichiometry, and these are reactants. These are C and D are product. So, this reaction tells you that A mole of A, reactant A, when combines with B mole of reactant B, it gives you C mole of C and D mole of product D. Okay. In that case, Kc is written as concentration of C power this number C, concentration of D power stoichiometry D divided by A power A, and concentration of B raised to power your B, whereas Kp is your pressure of C power C, P D equilibrium pressure of D power D, equilibrium pressure of A power A, equilibrium pressure of B power B. Again, I will like to emphasize that these are equilibrium concentration. So, we can simply write EQ, 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 and here EQ, EQ, EQ and EQ. So, these are the two terms which we came across in our first lecture. Once we know the concept of equilibrium constant, we can go and solve some equilibrium problems. Equilibrium problems. There are two types of equilibrium problem which we can come across. Your first is, suppose if I take this reaction, and if I know what is the equilibrium concentration of A, B, C and D, if I know this, then I will be told to calculate Kc, Kp or Kx. This is type 1 problem. Type 1 problem. There is another type in which Kc, Kp or Kx is given, and then we have to calculate equilibrium concentration or pressure of A, B, C, D. So, we will go one by one and try to see how to calculate your equilibrium, how to solve the problem. Let us look at this case. In this problem, what you need to calculate is equilibrium constant. So, question is calculate the equilibrium constant for the reaction below if they are present. They means these reactants or products A2, B2 or AB2 are present at equilibrium. Okay. So, what is given is 5 moles of A2 is present at equilibrium, 3 moles of B2 is present at equilibrium and 2 moles of AB2 is present at equilibrium, and also you have been given what is the pressure and temperature of the vessel. So, now question is to calculate Kc, equilibrium constant Kc, and we know this reaction is, we have to calculate Kc for this reaction. Okay. So, we know that Kc is equal to AB2, this is the concentration, you must remember this is the concentration, and you see number is 2. So, we will put 2. So, AB2 concentration of AB2 square divided by product product of these two concentration of reactants. So, the reactants are A2 and you can see that stoichiometry is 1. So, we will just put 1 and now concentration of B2 and here stoichiometry is 2. So, we will put 2. So, this is how we can calculate the value of Kc. Now, you see this what is given to you. The things which is given is number of moles of A2. So, you have been given Na2 is equal to 5 mole. Other thing which is given is Nb2, that is your 3 mole, and Nab2 is your 2 mole. Now, you see what we need is concentration of Ab2, not number of mole of Ab2, and we know the relationship between concentration and number of mole. So, concentration is equal to N by V, where V is the volume. Okay. So, we need to find out the volume, and for volume we can use your equation P V is equal to nRT, assuming that all reactants behave as reactant and product behave as an ideal gas, behave as an ideal gas. So, in this case we can simply apply P V is equal to nRT and V is equal to nRT by P. Okay. So, nRT by P, we know N is total number of moles of gases, which is in this case 5 plus 3 plus 5 plus 3 plus 2 is equal to 8 plus 2 10. Now, if we know, if we can calculate volume, we can calculate it because we know R is gas constant, N is 10, temperature is given 300 K and pressure is given, this is 300 K and pressure is given is 8.21 atmosphere. So, it is quite simple to calculate the volume. Once you know the volume, we can simply calculate concentration of A2. Concentration of A2 is number of mole of A2 by volume, and number of moles of A2 is your 5 and divided by V. And similarly, you can calculate your concentration of B2, which is NB2 by V, and that is your 3 by V. And then you can calculate concentration of your AB2. We know that number of mole of AB2 is your 2. So, just divide by V, V which we calculated from nRT by P, nRT by P. Now, we have the concentration of, we are able to calculate concentration of A2, B2 and AB2. Now, it is easier to calculate Kc. Kc is simply AB2 square by A2 into B2 square, and then you just put these numbers, you will be able to get the value of Kc. You will be able to get the value of Kc. So, now you can see that if equilibrium concentration is known, equilibrium concentration of reactant and products is known, it is easy to calculate your value of Kc. Now, in this problem, I will start with a heterogeneous reaction. In the previous question, it was a homogeneous equation. Homogeneous equation. Why I was saying homogeneous? Because your A2, B2 and AB2 was in gaseous phase. In this question, we will take an example of heterogeneous reaction. Now, you see this is your reaction. You can see this strontium chloride 2H2O is it in solid phase, while water is in gaseous phase, and this thing your SrCl2 6H2O is in solid phase. So, now you can see that there are 3 phases present, 2 solids and 1 gas, 2 solid and 1 gas. So, this is a heterogeneous reaction, and for that Kp is given 1 into 10 to the power minus 12 atmosphere minus 4. And then what you are needed to do is, what you need to do is to calculate equilibrium vapor pressure. So, you see this is the second type of question in which Kp is given, your equilibrium constant is given, and now you have to calculate equilibrium pressure. Okay. So, in that case you can simply start with Kp, and you see these 2 are solid phases, these 2 are solid phases, and so you can simply ignore that, and we can write Kp is equal to Ph2O. What is the power here? You can see at this point is 4. Okay. 4 is the stoichiometry of water in gaseous phase. So, you just simply put 4 here, and we know from the problem that Kp is equal to 1 into 10 to the power minus 12. And so, you can simply write Ph2O4 is equal to 1 into 10 to the power 12. Okay. I just did this way. Okay. So, you can simply write this, and then you will be able to calculate Ph2O, which is nothing but 1 into 10 to the power 3 atmosphere. So, you will be able to calculate equilibrium vapor pressure in this case if Kp is given. Now, let us take third question, and this came in 2016 for IIT Advanced. The question is thermal decomposition of gaseous X2 to gaseous X. So, it is basically dissociation reaction at 298 K takes place according to equation this. X2 is going to 2x, basically dissociation is happening. At the start of the reaction, there is 1 mole of X, X2 and no X. So, X2 is 1, initial mole of X2 is 1, whereas 0 is the your number of mole for X. Okay. So, you started with pure X2. As the reaction proceeds, the number of moles of X formed is given by your beta, sorry, this is beta. So, thus beta equilibrium is the number of moles of X formed at equilibrium. So, at equilibrium, the concentration of this X is your beta. The reaction is carried out at a constant total pressure of 2 bar, and then it is asking what is the equilibrium constant K p for the reaction at 298 K in terms of beta equilibrium. Now, you see here equilibrium concentration of product is given, equilibrium concentration of product is given, equilibrium concentration of reactant is not given. Okay. But you know initial concentration of, the initial concentration of your initial mole of reactant. So, what are known? Let us see here. So, we have X2 gas, this is the reaction to 2x gas. So, what is known is initial concentration. We know that this is 1 mole of X2 and no X means 0 this. And what we know add is your equilibrium concentration of this thing, and this is beta equilibrium. Okay. And now, question asks that what is the value of K p in terms of beta equilibrium. So, we know that K p is equal to pressure of X square, you see 2 here. So, this is a square divided by pressure of X2, pressure of X2, okay, pressure of X2. So, what we need to calculate is, and this is, you must remember, this is equilibrium pressure, what we are talking about is equilibrium pressure. So, first thing is we need to calculate your number of moles of X2, what is this thing, and once we know number of moles of X2 and number of moles of X, then we need to calculate mole fraction of X2. So, this is your mole fraction of X2 and mole fraction of X, and then finally, we can calculate your K p. So, let us go and see. So, first step here is your calculation of equilibrium concentration of your X2. So, let us write this initial, you have 1 mole 0 and at equilibrium you have beta. Okay. Now, what is the number of mole of X2? This is the first question. Okay. So, the way you can do is just by looking at the reaction and number of moles of X formed at equilibrium. So, what this reaction tells you that if 1 mole of X2 is used, 2 mole of X will form, 2 mole of X is formed. Okay. or you can just think in a opposite way. If 2 mole of X is formed, 1 mole of X2 is used. Okay. So, if I think in this way, now think of this, if beta mole of X is formed, how many moles of X2 will be used? So, I told you 2 mole of X, 1 mole of X2 used, am I right? 2 X formed, 2 mole of X formed means 1 mole of 2 mole of X formed, 1 mole of X2 is used. So, 1 mole of X is formed, in that case half mole of X2 will be used, and beta mole of X is formed means beta by 2 mole of X2 will be used. So, what is the equilibrium mole of X2? You started with 1 mole of X2 and now you know that beta by 2 mole of X2 is being used. What does that mean? What is left out? You started with 1 and used up is beta by 2. So, left one is 1 minus beta by 2. So, this is 1 minus beta by 2. So, I hope this is clear. You must first calculate how much mole of X2 is at equilibrium, and that you can do by using the fact that beta mole of X is formed and 2 X mole of 2 mole of X is formed from 1 mole of X2. So, what we have calculated is the equilibrium concentration for the reaction. So, X2 gas going to 2X gas. This is the reaction and we already calculated what is the equilibrium concentration or number of moles at equilibrium. So, this is 1 minus beta by 2 and this is your beta. 1 minus beta by 2 number of moles of X2 and beta mole of X is present at the equilibrium. So, now we need to calculate Kp, and for that we need to know partial pressure of X2 and partial pressure of X. So, partial pressure of X2 is equal to mole fraction of X2. So, this is mole fraction of X2 into total pressure. And what is mole fraction? Mole fraction is your N of X2 divided by total number of gaseous molecule multiplied by P. What is NT? Total number of molecule is number of molecule of X2 and plus number of molecule of X, number of mole of X. So, NT is equal to 1 minus beta by 2 plus beta, and this is equal to 1 plus beta by 2. So, your Px2 is equal to Nx2. Nx2 is 1 minus beta by 2 divided by total number of molecule is 1 plus beta by 2 and into P, whereas Px is equal to Nx by Nt into P. Nx is your beta. So, beta divided by Nt is your 1 plus beta by 2 into total pressure. So, now we know what is Px2 and we know what is Px, we can calculate what is Kp value. Okay, so, now we can calculate Kp, and Kp for this reaction is pressure of x square divided by pressure of x 2, and just we calculated pressure of x. Pressure of x is your beta by 1 plus beta by 2 into p, and this is whole square divided by 1 minus beta by 2 by 1 plus beta by 2 into p. So, this is equal to K p is equal to your beta square by 2 plus beta by 2 square into p square divided by your 2 minus beta and 2 minus beta divided by 2, 2 plus beta divided by 2 into p. P cancels out, this term cancels out, this 2 cancels out. So, what you are left with is your beta, sorry, this is your beta. So, this is beta square by 2 plus beta square into this 2 goes up. So, 4 into p divided by 2 minus beta, this 2 plus beta goes up, 2 plus beta, that is all, 2 plus beta and this square terms cancels out. So, what you are left with is 4 p beta square by 4 minus beta square, and since p is equal to 2 atmosphere, you can simply write 8 beta square by 4 minus beta square. Okay. So, this type of question can also come in which initial concentration is known, one of equilibrium concentration of one of the product is known, and then you need to calculate K p. You can easily do that. First you need to calculate equilibrium concentration of the reactants for which equilibrium concentration is not known, and then you can simply calculate the value of K p. So, in this question you have to you have been given equilibrium concentration of A, B, C. The reaction is A going to B plus C, and equilibrium concentration is known 4.6, 2.3, 2.3 moles per liter at 25 degrees Celsius. If 2 moles per liter of A are removed, calculate the equilibrium concentration of A, B and C at same temperature. Okay. So, it is going to utilize, it is basically a mixture of type 1 and type 2 questions, mixture of type 1 and type 2 questions. In this, first we have to calculate K p or K c, and then you disturb the equilibrium by removing your A, and then you need to calculate equilibrium concentration of A, B, C, and here you can utilize the fact that you have already calculated K c. So, let us think of this question. So, reaction is A going to B plus C, okay, and equilibrium concentration is known, equilibrium concentration is given, equilibrium concentration is given. This is A is 4.6, B is 2.3 and C is 2.3. So, value of K c will be what? Simply concentration of B into C divided by A, is quite simple to calculate, and you can do B is 2.3 into 2.3 divided by 4.6. Okay. So, this is quite simple to calculate Kc, but now question is that that 2 moles per liter of A is removed. So, basically this is equilibrium. What you are going to do is you remove 2 moles of this, 4.6 minus 2. What happens in that case is now it is no longer at equilibrium, no longer at equilibrium. Now, reaction is no longer at equilibrium. Now, question is which side it will shift. Okay. So, 4.6 minus 2 and then you have 2.3, 2.3, this side 2.3, but equilibrium is now disturbed. So, at equilibrium what can happen? This is your 2.6. Okay. So, suppose reaction basically goes from this to this side. Okay. In that case what will happen? You can simply write 2.3 minus x, suppose x mole of C reacts with x mole of B and x mole of A is formed. This is at new equilibrium. Okay. So, in this case Kc is equal to your 2.3 minus x square divided by square, because you are multiplying concentration of B with concentration of C. So, 2.3 minus x square and divided by 2.6 plus x, 2.6 plus x, and this you have already calculated, that was 2.3 square divided by 4.6. Now, you see you have an equation, there is only one unknown and you have one equation. So, you will be able to calculate x, you will be able to calculate x, and so you will be able to calculate x, then you can just put it here and now you know what will be the equilibrium concentration of A, B, C. Here I told that reaction will go to your left hand side or reverse reaction will take place. How you can tell that? It is quite simple. Here we know that Kc is equal to B into C by your A. What we are removing is this one. Okay. If you take out A, this Kc is constant. You must remember Kc is constant. Okay. Kc is constant. Okay. So, if I remove A, then what will happen? Concentration of B and C will decrease. So, that B into C by A remains constant, and that is why B and C, when B and C can decrease, when reverse reaction will take place. And so, we can simply write that C is decreasing by x amount. So, B will also decrease by x amount, both are reacting, they must react in the same stoichiometry, and so if concentration decreases by x for B and C, concentration of A will increase by x, and so you can simply write 2.6 plus x, 2.3 minus x, 2.3 minus x, and so Kc can be calculated. Okay. So, this is about the problem which can be solved using concepts from your equilibrium constant. Okay. Now, let us talk about another important term in chemical reaction, which is called reaction quotient. I have already introduced this to you, but now I will again define and then finally, I go and tell you what is the importance of this term. So, I told you that if I start with some reactant A, I am talking about a reaction A going to B, and suppose we start with reaction A, only reactant A in the box, and what will happen is this will convert to B first. Suppose one of A went to B, this is your B. Then I wait for some more time and then we get your one more molecule goes to B. Again wait for some time, one more molecule goes to B, suppose. Okay. After some time what will happen is that this now does not change. If I suppose wait for few more hours, and what you are able to see that there is no change, in that case what we say that this we have reached the condition of equilibrium. Okay, condition of equilibrium, and your B by A, which is B equilibrium by A equilibrium, which is basically 3 by 3, this is 1, and this is your Kp of this reaction, Kc of this reaction. Here you must keep in mind that this is the equilibrium concentration of B by A. So, this is concentration at this point, not at this point, okay, because in this state equilibrium has not reached. So, this is not the equilibrium concentration of A and B. What is this is your Q, reaction quotient, and that is again equal to B by A, but now this is not a concentration at equilibrium, this is concentration at any time. Okay. So, Q changes with time, Q changes with time, and at this point Q is equal to 1 by 5, 1 by 5. Q is different from equilibrium constant, is that equilibrium constant is fixed at one temperature, while Q changes with time. So, suppose I start with pure A, and so you have pure A quantity, pure A, then what will happen? Suppose reaction is going from A to, this is your extent of reaction, it is going from here to here, and this is somewhere is the equilibrium constant. Okay. So, in this side, the reaction quotient product by reactant. So, before reaching equilibrium, your reactant is more in number, while product is less, In this case, Q will be, if I compare with P equilibrium, by R equilibrium, R equilibrium, what we expect is your product, since product is less, reactant is high. So, this quantity is smaller than this. So, Q is less than your K before equilibrium is reached. Now, what happens is if I start with pure B, in that case again there will be some time at which only one of product has gone to reactant. So, in this you see this we are starting with B and this is your A. So, in this case Q is, I am again calculating only Q for a forward reaction. So, I am not going to change this B by A. So, B by A will be your 5 by your 1, and now Q is greater than K. In this case your reverse reaction will take place. So, we have three different conditions. One is Q is your less than K, then reaction will proceed in forward direction. Q is equal to K, then your equilibrium is established, and Q is greater than K implies a reverse reaction will take place. Reverse reaction will take place. So, if I plot reaction quotient Q with time, you get this kind of curve. This is Q is greater than K and this is for Q is less than K. Q is your product by reactant. So, Q is decreasing. What does that mean? Product is converting into reactant. So, reverse reaction is taking place. Reverse reaction is taking place. Reverse reaction is taking place. While if Q is less than K, then Q increases with time. Q increases with time, and when Q will increase? When P increases and R decreases, and this means forward reaction. So, this is for forward and this is for reverse reaction. And this is being used to know whether a reaction will go in a forward direction or reverse direction. So, simple thing is, if reaction quotient is greater than K, then reverse reaction is spontaneous. If reaction quotient is equal to K, then your reaction is at equilibrium. When reaction quotient is less than K, then your forward reaction will proceed. Forward reaction will proceed. The another graph which we can think of is G versus extent of reaction. Extent of reaction. So, suppose you have G of A is here, G of B is here, reaction will like to take place. What we expect that this should go down like this, but this does not happen, and that is basically why equilibrium exists. And I told you that there will be a deep, and this deep, the minima will be obtained at equilibrium, and this minima is due to delta G of mixing when A and B is getting mixed. A and B is getting mixed. When A and B gets mixed, entropy increases, and so delta G makes a contribution to your total delta G. What do we mean by delta G? Is basically if I go from here to here, delta G is less than. So, till this point your delta G is, you can see B G B minus G A, delta G is or less than 0, and in this regime delta G is greater than 0, and so reaction will go from B to A. In this regime reaction will go to A to B, and this is the when Q is less than K, and this is when Q is greater than K. So, reaction quotient is less than K, then forward reaction is taking place, and reaction quotient is greater than K, then it is not reverse reaction is spontaneous, and at this point where Q is equal to K, we have equilibrium. So, there are three very important points. First is when Q is less than Kc or K, your reaction will proceed in forward direction. Reaction will proceed in forward direction. Second, when Q is equal to K, then reaction is in equilibrium. And third is Q is greater than K. Reaction will proceed in reverse direction. So, reaction quotient and Q, reaction quotient and quotient is Q, and equilibrium constant K can be used to know the direction of the reaction. Direction of the reaction. For example, take this case A going to B, and suppose I know that K equilibrium constant K c is your value is 4, and suppose in a reaction mixture we have 2 moles at certain time t, or you are putting suppose 4 mole per liter of this and 2 mole per liter of this per liter of B. Now, can we predict whether reaction is going in forward direction or reaction is going in reverse direction? We can do that since we have Kc and we know the value of Q. In this case, Q is what? 2 by 4, and so Q is your half. You see here what is Kc? Kc is 4. So, Q is your less than K. Q is less than K, and so reaction will proceed in forward direction. Reaction will proceed in forward direction. Now, you can take another case, A going to B, and suppose Kc is half, and if I take a box which has box and add suppose 2 mole of A and 4 mole of B, and then I want to know whether A will convert to B or B will convert to A. What we need to do is simply calculate the value of Q, and Q is your simply B by A, and this is your 2. So, 4 by 2. So, 4 by 2 is 2. Now, you see Q is greater than Kc, and so the reaction. So, basically your reverse reaction will proceed. So, more B will be converted to A, and what you will get is 4 minus x, 2 plus x, and you can calculate what is the amount of x converting by simply adding using Kc. Kc is equal to 4 minus x by 2 plus x, and that should be equal to half. So, first thing we can simply know in which direction if we mix A and B, in which direction reaction will proceed, whether in from B to A or A to B. And if I know the value of this, we can know by comparing the value of K and Q. And if I know the value of K and Q, value of K and concentration of A and B, we can also tell that how much A goes to B or how much B goes to A if reaction goes to A, if reverse reaction is happening, if reverse reaction is taking place. It is very, you just see just simple two concept of Kc and Q, we are able to tell not only we are able to tell direction of reaction, but we are also able to tell, we will be also able to tell how much your reaction, how much your reaction will go in forward direction or reverse direction So, there is, we will be able to calculate that how much A goes to B or B goes to A, how much A goes to B or B goes to A. So, here we will stop in this lecture. In next lecture, we will discuss about Lee-Chatelier principle. Thank you very much.